unlike a normal wrench, inside of it there's a mechanism in here to measure the amount of torque that's been applied to the bolt. This is very useful for a number of applications, including automotive, where the specified torque, the clamping torque of the bolt has to be known precisely. There's a lot of elements that go into the design of this. First of all is the material selection. The bit here is made of chrome vanadium steel, and the rest of the tool is also made of chrome vanadium steel, 6150. After it's drop forged to be made into shape, it's annealed, quenched, and then tempered to give it the maximum possible strength and hardness. Obviously, the actual physical design of this has had a lot of thought put into it. It's very long and heavy to ensure that lots of torque can be applied. And a lot of thought has been put into the ergonomics of it, such as this plastic handle.
Hello there, it's Gabriel, and I'm going to be talking about the functional and design requirements of a torque wrench. So if you've ever used a torque wrench before, you'll be aware that the main function of a torque wrench is to tighten bolts and fasteners to a desired torque, right? So it measures torque, basically. So having said that, I guess the functional requirement or constraint of this torque wrench would be that the material has to withstand the torque required to tighten these bolts, yeah? So we took that into consideration when making our MPI and selecting the materials to use. But the problem with this is there's so many uncertainties involved when determining the amount of torque required to tighten the fastener, because there's so many things you have to look into. So the fastener could lose lubrication, could become corroded, could seize, and then also the removal torque of a fastener is actually 300% more than installation torque. So you might calculate the torque of a wrench after you've made it, and you still need a strength higher than that because the removal torque is greater than that, right? So that was for the functional requirement. Yeah, it has to withstand the torque. Then we went into the geometric requirements, and then what we did, we restricted the diameter of the torque wrench because, well, we want the torque wrench to be able to we want to be able to hold the torque wrench, right? And we actually did some research, ergonomics and everything, and we discovered that the best, for a power grip to produce maximum torque, we need a handle that has a diameter of, let's say, about 30 to 50 millimeters. So we picked around 40 millimeters as the constraint for the diameter. And also we thought, since more length kind of increases the torque, so the longer it is, the more torque it has, which is why you have torque wrenches of almost 4 feet long. So what we did, we just picked the least, the shortest torque wrench we could use, which was about 190 millimeters, because we need to consider the handle you're going to use to grip it. And we made the objective of this project be to minimize the cost of the wrench, because you will probably find a lot of materials that can serve these purposes, but at the lowest cost, because it's not like anyone's looking for a Louis Vuitton wrench or anything. So we need a low-cost wrench that's going to provide the torque required, and at the same time have the required diameter and length. Well, I just don't know how we can put that in our MPI.
Well, Gabriel, I'm glad you asked. Because you see, we can actually do a mathematical performance index to figure out how to minimize the cost of the torque wrench. So we start with basic physics, and we say that our minimum stress value is going to be force times length divided by volume. This comes from the fact that stress is equal to force divided by area, and this is just basic geometry. So from this, we can do a little trick of mathematics and say that the variable d is equal to cost divided by volume. And you get this if you're just going to buy materials anywhere. You'll get a certain volume of any kind of material at a certain cost. So this is a very reasonable measure to use. And then using this, we can then derive the cost and say that it's greater than or equal to FL times our variable D, all divided by the minimum sigma, by the minimum stress value here. Now if we take all these numbers and put them on a graph, like this, and now assuming that our sigma minimums can be around 0.79 GPa, which is reasonable given the constraints you just gave us, that means we're going to have a line going across this graph right here, and everything beneath that line is cut off. So that means that cement, that wood, that cork would all fail if we use them in a torque wrench. And only the materials that are left above this line will actually be able to withstand those stresses. Since cost is increasing as we go from left to right, that means we want to select the material that's furthest to the left right here, which in our case is going to be a medium to high carbon steel, unalloyed.
But wait, I could think of a couple functional factors that the MPI doesn't really take into consideration. And I'd argue in fact that they're just as equally important as those that it does. And in fact, I can name a couple of those off the top of my head. To start, fatigue resistance, corrosion resistance, temperature range, and manufacturability are just a few that I can think of at this point in time. I mean, high carbon steel is pretty hard to manufacture, and it also won't function properly at high temperatures. Not to mention that it corrodes quite quickly compared to other options. And taking these into consideration as well as the factors that are presented by the MPI, Martin Industry decided that 6150 steel is the best option, also known as chromium vanadium steel. And that is what's most commonly used today to produce torque wrenches.
I do see your point, but I feel your premise is quite wrong. Because yeah, sure, chromium vanadium steel, I see why the designer would choose it, because chromium provides corrosion resistance, which is quite desirable in torque wrenches, because you'd have to be tightening bolts, and you don't want the end to be corroding, right? And then you also give that shiny exterior, and then it makes it easier to clean. So yeah, chromium is essential alloying element in the steel. I do see that. And then also improves hardenability. Chromium and vanadium do improve hardenability. So, but however, I feel that fatigue resistance, I feel our material does cover that. And the temperatures at which the torque wrench will be operating at does not account for this factor because, well, our material is well within its temperature range, so I think that is covered. However, 6150 steel, I feel it's a bit, I don't know, I just wouldn't pick it. Maybe 01 steel, because that also does provide corrosion resistance and is manufacturable. So that wouldn't be my choice. 6150 steel is, I don't think that's it.
Yeah, I kind of agree with you. I don't think I'd pick 6150 either. In fact, after some research that I went through, I think that the best option would be Malaysian steel, and in fact, grade 350 Malaysian steel. Now, this stuff's amazing. Like, it doesn't corrode quickly. It's super strong.
Yeah,
it's pretty light.
Problem is though that's expensive. I mean, if you did look at MPI cost, minimizing costs is the main the main objective, because I mean, you're a workman. Why would you want to be buying such expensive materials? Yet, 01 steel will perform the same functions. As a matter of fact, you can as well use medium to high carbon steel even, because it's cheap and performs the function. So, best case scenario, as a designer, considering all this and the requirements you need for a torque wrench, I would pick 01 steel. Simple.